Welcome. Today we cover numerical integration. Let's revisit quickly Riemann sums. We have seen Riemann sums with equal spacing like this. We have a maybe interval from 0 to 1, and then we have a 1 over n, 2 over n, etc., n minus 1 over n. And then what we have done is we have looked at the left point here, the function value here, and then evaluated it at this point and multiplied by 1 over n, and taken the next point here, which is here, evaluated it the third. Always took the left side and finally here the last. So what we have seen is we have approximated the area under the curve using a collection of rectangles, and let's just do that. And what we have seen is that the integral, so the integral from 0 to 1 f of x dx is a limit of sums, and the sum is just always multiplied by n, 1 over n, the sum, and then we take k equal to 0 to n minus 1, and then we take the f of k over n. So that was a Riemann sum. And we have defined the integral as a limit of this Riemann sums. Let's generalize this slightly. Sometimes it's useful that we don't insist on equal spacing. Maybe we start here with x0, x1, maybe x2, x3, x4, etc. until we have xn. And the function here, maybe let's give the function like that. And given what we have now is, again, we can just take the left point and compute this, look at this rectangle here. Now we have the next rectangle here. It starts here, goes, it's a shorter one, more narrow rectangle, and it's a longer one, and take this, and finally orange. So let me just write down again expression. What we have here is we have a sum, and so this is n minus 1, so we go from k equal to 0 to n minus 1, and then we take f of x of k. And now we take the difference between the xk plus 1 minus xk. So this is a more general Riemann sum, generalized Riemann sum. And sometimes it's useful, for example, if the function is more complicated in some places, you want to make the grid more narrow, and in places where it is kind of boring, you make the spacing larger. So this is more flexible, and it's also what Riemann really did. This is the Riemann definition of a Riemann sum, and what we have done with the equal spacing was Archimedes, already Archimedes definition. When we do a Riemann sum, we can evaluate the function at the left. So that's what we usually did so far. Let me just do that first with green. So that's a left Riemann sum. We can also evaluate the function. Let me just write this down. So we have the left Riemann sum. It's sum f of xk delta xk, k equal to 0 to n minus 1. And as before, the delta xk is xk plus 1 minus xk. So that's what we have done here. This green area is the left Riemann sum. But we can also evaluate the function at on the right hand side. So if we evaluate it here, we actually have this function. Here it's kind of almost the same. Here we get it like that. And here we get it. So this is a left Riemann sum. Now if we evaluate, we do the same thing, but we evaluate the function at xk plus 1, and then we take delta xk. Then this is called the right Riemann sum. Now you see, kind of a better approximation is to take the average of these two. Actually take the average of fx k plus 1 and f of x of k, and if you average these two things, we get a nice trapezoid here. So also here it's essentially the same, but here we get this. I have to use it. And also here we have just we are already very close to the function. So this red area is, so if this is the left Riemann sum and this is the right Riemann sum, what we can do is we can take the average of these two. So if we take L plus R half, this is, let's just call this our new sum here, is the sum of areas of trapezoid areas. And it approximates it better than the left Riemann sum or the right Riemann sum, as we will just see in an example. As an engineer, you want to make integration as effective as possible and with a minimum number of summations. What we can do, and what Simpson did, is we can take the midpoint here, call this yk. Now we sample the function at 3 values. We sample it here, so that's f of x of k, and then we sample it here, which is f of x k plus 1, and then we sample it also in the midpoint. But so we have one point more to evaluate, but then what we take is we take our contribution, which we take is f of x of k, and we take 4 times we take this with a higher weight here, the middle point, so plus 4 times f of yk, so that's the midpoint here, and so yk is xk plus 1 minus xk plus xk over 2, midpoint, and then we take again plus fxk plus 1. And then we have to divide it by 6. So that's what we take, and then we take so this is kind of our new function value, and then we take the delta xk as before, and we sum that up over all k. So that's the what we call the Simpson rule. It turns out that this rule is exact if the function is made of parabolic pieces. Like the Simpson rule would have been exact if it would have piecewise linear pieces. Let me just take therefore the I take the square function. I take the square function fx is equal to x squared. This is 1. This is fx is equal to x squared. And let's just take our kind of the simplest case where we have just one interval which we are considering, right? We take here this is our x0, this is our x1, and then we have a midpoint here which is our y0. So let's just see what we get when we take this sample. So we take the sample here, which is so the delta x here. That's of course 1, and so what we have is what we have to take is the f of x0 plus 4 times f of y0, and again the y0 is just the x0 plus x1 over 2, that's just 1/2, and plus fx1, and then we divide the whole thing by 6, and then we multiply by delta x0, and we can evaluate this. So in this case the Riemann sum has only one term, but this term is kind of an average of sampled points here. So we have evaluated it here, which is 1/4, and then we have evaluated it here where it is 1, and then we have evaluated it here where it is 0. So let's just see. So that's equal to 0 plus 4 times 1/4 plus 1 times 1, so 1, and then divided by 6 times 1. So what we get is, this is 1 plus 1, this is 2/3. This is 2 over 6, which is 2 over 6, which is 1/3. And as it happens, this is actually just what we know, right? The area under the curve is, if you integrate from 0 to 1, x squared dx is x cubed third evaluated from 0 to 1. That's equal to 1/3. So yes, so in this case we really have already with one kind of summation part, we have already got the right result. Now this is already kind of fantastic. So this is already good enough for most numerical things which you are doing. But people have refined this. You find that on, if you look it up, there are many different generalizations. Let's just look at another one which is fun before we go to the Monte Carlo. What we can do instead of just dividing into kind of take a sample point in the middle, what we can do is we can take 2 sample points. So this is just 1/3 here, 1/3 we divide it into 3. Let's call this yk and this zk. And now if you have the function, if the function is given, right, what we can do is we can sample it here. So this is and then we can sample it here, we can sample it here, we can sample it here. And then we can take an average of these samples. That's an engineer who's kind of interested. What is the best average of samples here which we can get? And this is the Simpson 3/8 method. So what we can do is we can divide it into 3 pieces, and then we can take the weights which we take now are the weights 1, 3, 3, 1. So we weight them heavier. Before we had 1, 4, 1. We had 1, 3, 3, 1. We weight them a little bit heavier here in the middle. And so what we can take is we can take xk plus 3 f of xk plus 3 times fyk plus 3 times fzk plus fxk plus 1. And then we divide everything because we have taken kind of 8 weights here, so we have to divide that by 8. And then we multiply with again with delta xk, and so that's our integration method. It's slightly better than the other one, than the previous one, but we have to pay also the price that we have to evaluate the function at 2 values in the middle and not only 1. Let's look at it also in the case of the square again. And now we take the values 1/3, right? We evaluate it at 1/3, 2/3, and we sample the function at here, 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 and here. So what we have to do is we have to take f of 0 plus f 3 times, so we have 3, right? So that's this 3/3. So we have 3 times f of 1/3 plus 3 times f of 2/3 plus f of 1. And the whole thing divided by 8. And the delta, this is if this is equal to x0 and this is equal to x1. The delta x0 is just x1 minus x0 is equal to 1 in this case. So we have the times delta x0. So these are the terms, these are the if you make a lot of intervals, kind of each interval has this contribution. But let's just see what we get here. So we have a 0. F of 1/3 is 1. So this is 3. 1/3 square is 3/9. 2/3 gives us 4/9. So this is plus 3 times 4/9. And then F1 is 1 plus 1 over, that's just 1. No fraction here. And then the whole thing is divided by 8. So what do we get here? So we get 3/9 plus 12/9 is 15/9 plus 9 is 24/9. And then divided by 8, right? So what we have is, this cancels here, this is 3/9. So this is 1/3. And again we have a match. We have again a match between the actual area and this numerical value. So this is a fantastic method for integration. It's very, very flexible. It works in any dimension. It works very reliably, and it works also if the function is not very well known. It works in very complicated situations. Let's just look at let's just look what we do here. So let's assume the function is between 0 and 1, and we have a function here. Now, instead of organizing the points here, regular lattice or some spacing, predefined spacing, what we do is we just take random points. So let's assume xk are random points. chosen according to the normal the uniform distribution here. So so we pick just a random number here, just throw a random number here, evaluate the function. So let's just see, kind of, I have here, this is x1 here. I take my function value, and then I pick another one I get here, and then I get another function value. So this is x2. And so on. I randomly just pick some third number, and I get x3, etc. So I'm doing that, and then I'm taking the sum s n is 1 over n. In general, if the interval is kind of a here and until b, we would also multiply here with b minus a, and then we take the sum k equal to 1 to n f of x k. So these are random numbers, and it turns out, just by the law of large numbers in probability theory, that this converges to the interval from a to b f of x dx. So this is the Monte Carlo method, and so it's a random sum, and it's actually much more powerful than one would expect, because this is actually a Lebesgue integral. Much nicer than the Riemann integral. The Riemann integral is not suited for kind of more advanced topics like in probability theory, statistical, stochastic processes. So this Lebesgue integral is much better. But let's just take the function f of x is equal to sinus x. And let's take pi here, so that the function is this function here. And we know that we want to compute the area under the curve here. We know that the integral from 0 to pi sinus x dx is equal to 2. We have done that before. But let's just do what I will do is I take here this is a is equal to 0, b is equal to pi. So what I take is pi over, let's just take 5 points, and then take the function value. So let's just see, we have 5 points here. So I take xk, and this is sinus of xk. Yeah, the sum is a little bit too small. So the sum here, the sum pi over 5, sum k is equal to 1. So this is 1, 2 until 5, fxk is actually, in this case, is equal to 1.25, which is way too low. But of course we can do that with a computer. I can take the same thing. I can take 50 values instead of 5 values, and then see what we get when we take that. So when I take 50 values here, so n is equal to 50, I got already 2.085. And let's just see what happens when I take 500 points. So I take 500 random points here, and I evaluate that with divide by 500. So what I get here with 500 points, n equal to 500, I get a value of 1.986. So it doesn't converge too fast. So the Simpson and even the trapezoid method and even the Riemann sum is better. But that works also in situations where the function is quite crazy. Okay.